All right, this is part 2 of the 3A review, picking up with number 13. So it says find the zeros of the given function. Anytime I see that, that means I'm looking for when does x equal 0. And for us, the first thing you should always check to see if it's factorable. So I'm going to try to factor by trying to pull out factor by grouping method. So if I pull an x squared out of the first pair, that would be an x plus 2. If I pull -9 out of the second pair, that would also make x plus 2. So this looks very promising because it looks like we're going to get something factorable. Hang on just a second. Because we can then pull the x plus 2 to the front. So if we pull that x plus 2 to the front, we'll be left with x squared minus 9, which is factorable again. So x plus 2 times x plus 3 times x minus 3. And to find the zeros, we set f of x equal to 0, and we solve for the x's. So this would be -2, -3, and +3. So there are my zeros of this function. So if it's factorable, it's not that bad to find the zeros of the function. Now, not everything is going to be factorable. And sometimes we'll want to know a little bit about the types of zeros we should expect as possibilities before we try to do any other techniques. And that's where Descartes' rule of signs come in, because it allows you to determine what types of possible solutions you can get to a problem. So the way it works is that to find the number of possible, positive, real zeros, we're going to examine the number of sign changes in the original function. To find the number of possible negative real zeros, we have to look at f of -x. So we'll look at that one when we get to it. So for f of x equals x cubed plus 6x squared minus 7x minus 3, the number of times we change signs or variations in signs comes when you look from one term to the next. So this is a positive to a positive, which is not a sign change. But this right here is a positive to a negative, so that constitutes a sign change. So I'm going to put a little number there that says that's a sign change. This one is a negative, and it's staying negative. So there's only one sign change throughout the terms from the highest power down to the lowest power. So that means the number of possible positive reals is just 1, or typically you would subtract off pairs to stand for imaginary number pairs, but since if we subtract 2, we're going to get down to a negative, so it's just going to be 1. Okay. Now when we look at f of -x, that's going to be -x cubed plus 6 times -x squared minus 7 times -x minus 3. -x cubed would be a negative. -x squared would be positive times a positive would still be positive 6. Negative times a negative is a positive 7x, and then we have our minus 3. This time we go from a negative to a positive, which is one sign change. We go positive, positive, which is not a sign change, and then we go from positive to negative, which is another sign change. So for the possible negative real numbers that could be solutions, there are 2 sign change variations, so that's 2, or if you subtract off an imaginary pair, that's kind of how I think of this, 0. So one possible real solution that's positive, and either 2 negative real solutions that are possible, or there'll be no negative real solutions and there'll be 2 imaginary possibly. So that is what Descartes' rule of signs tells us. For this next one, we're going to do the same thing. So I'm going to do this one a little bit quicker. So I'm just going to count my sign changes here. So there's 1, negative stays negative, negative goes to positive, so there's 2. So for possible positive reals, it was 2 or 0. For f of -x, this would be 2 times -x to the 4th minus 6 times -x squared minus 2 times -x plus 9 that would be negative to the fourth is still going to be a positive, so that's 2x to the fourth. Negative to the second power will still be a positive, but then we times it by the negative, so it's going to be negative 6x squared. Negative 2 times negative x would be positive 2x, and then a plus 9. So here there's only one sign change from a plus to a minus, and a minus to a plus, so that's 2, and then a plus to a plus, so that's just that. So this would be possible negative real solutions is going to be 2 or 0 as well. So what could happen here is that you could have 2 positive reals and 2 imaginaries. You could have 2 negative reals and 2 imaginaries. You could have 2 positive reals, 2 negative reals, or because of the 0 cases for both of them, you could have 4 imaginary solutions. Now only one of those is going to be the right answer to the zeros of this polynomial. But what Descartes' rule of signs does is lets us see the possibilities of what could happen. And we have to actually solve it to figure those out, or at least attempt to solve it. So the way we attempt to solve for zeros of a polynomial that may not be factorable by our techniques we learned in Chapter 1 and Chapter 2 when we were back first in the beginning of the semester is that we're going to do something called the C's over D's list. That's our potential rational roots. Now the only problem with this method is if you don't have any rational zeros of the polynomial, if all the zeros are imaginary, or if they're like square roots of 3 or something like that, if there's not a single rational zero to the whole polynomial, then this method's not going to help us to factor it down and get our answers. But for the ones we're going to do, we're going to be able to break it down. So just realize this is not a method that's going to solve every single situation that you get to. So my C, when we talk about the potential rational zero list, C is related to the constant term at the end, and D is the leading coefficient. So the way you get your potential list to try is you list the factors of C over the factors of D, and you have a plus or minus in front. So this is factors of C. Now factors of C are 18, so that'd be 1, 2, 3, 6, 9, and 18. Those are all things that divide to make 18. Factors of D are just 1 and 3. To get your list, you put each of these C's over each possible D. Now, some people do all of them over 1 first, and then some people do 1 over 1 and then 1 over 3 and go through that way. Some people worry about putting them in order from least to greatest. You do whatever your instructor tells you to do. I don't get too nitpicky about the order. I just want to make sure you've gotten all the combinations. So 1 over 1 would just be plus or minus 1. 2 over 1 would be plus or minus 2. 3 over 1 is plus or minus 3. 6 over 1 is plus or minus 6. 9 over 1 is plus or minus 9. 18 over 1 is plus or minus 18. Then we do everything over 3. If a number repeats, we don't list it again. So 1 over 3 is new. That's 1/3. 2 over 3 is new. 3 over 3 is 1, which has already been listed. 6 over 3 is 2, which has already been listed. 9 over 3 is 3, which has already been listed. And 18 over 3 is 6. So only 2 new ones popped up from that second round of listing. So you don't need to repeat them more than once. So there's a total of 1, 2, 3, 4, 5, 6, 7, 8 times 2, because there's all plus or minus cases. There's 16 potential rational zeros there. Okay, so why did we teach you that? Well, because to solve the biggest problem on the test, one of the ones that there's 2 types on the test that take the most time, finding all the real solutions of an equation that's not factorable using our technical methods from Chapter 1, and graphing some rational equation functions. So those 2 things are our biggest topics. So that's what the remaining problems of this review are. So if we want to find the solutions, the real solutions of this equation, notice that we can't factor by grouping here. It's not going to give us a matching parentheses. So the first thing we would try is our C over D list. So C's here are factors of 30, which would be 1, 2, 3, 5, 6, because 5 times 6 is 30, 3 times 10, 2 times 15, and 1 times 30. My D is 2, so that's my leading coefficient, so factors of that are 1 and 2. My C over D list is plus or minus, and some people don't write the whole list, each one with a plus or minus. They do it like this, and that's fine. So this would be 1 over 1, 2 over 1, 3 over 1, 5 over 1, 6 over 1, 10 over 1, 15 over 1, 30 over 1. Then we do our other part. 1 over 2 is new, 2 over 2 is 1, 3 over 2 is new, 5 over 2 is new, 6 over 2 is 3, 10 over 2 is 5, 15 over 2 is new, and then 30 over 2 is 15. So notice the plus or minus is in front of all of these. So then we typically start by a systematic approach that I like to use is I start with +1 and -1, and I use synthetic division to try to see if this goes in equally, which means I'm looking for a remainder of 0. We're trying to factor down at least 1 degree of the polynomial. So if I start out with 1, and I place my polynomial up here, making sure no missing powers are there, and we have all of our terms, so that's good. Let's see if this goes evenly. So I pull down a 2, multiply, add the column, multiply, add the column, multiply. I don't even worry, it's not 0. So this is not a good one. Then I try -1. So 2, -3, -17, and 30. Now, if you want, you can write down this number. This was 12 to see what's closer, because that sometimes helps you figure out which way to go next. So this is 2. Then we multiply, add the column, we multiply, add the column, we multiply, and that's much further away. So honestly, I don't think I'm going to try another negative right away. I'm going to go back to the positives because they were a little bit closer to 0. So let's try 2. And again, this is just my method of how I rationalize what to try next. Everybody has their own techniques. So bring down the 2, multiply, that's 4. Add the column, multiply, and there we go. We got lucky. So there's my remainder of 0. So what I know for a fact, what this actually tells you, is that this right here is a 0 of that polynomial because it has a remainder of 0. That means it would have been tied to the factor of x minus 2. Okay? So what we've done is we've said now this is been pulled out to the front. This is 1 degree less than what we started with. So that would be 2x squared plus x minus 15, and we're still trying to solve it equal to 0. As long as this is quadratic, you don't need to do another round of c's over d's. You can just use the quadratic formula to find the other two zeros. So let's do that. So I already know for my zeros over here, this is my final blank, that +2 is one of those lists. Okay. Now I'm going to take 2x squared plus 1x minus 15, set that equal to 0, and try to solve it. So x equals -b plus or minus square root b squared minus 4ac all over 2a. So that is -1 plus or minus, that would be, let's see, 8 times 15. They're both negative, so that comes out positive, plus the 1, so that's going to be 121 over 4. So this is -1 plus or minus 11 over 4, because square root of 121 is a perfect square. Then we need to break that into both cases, so that's -1 plus 11 over 4 and -1 minus 11 over 4. -1 plus 11 is going to be 10 over 4, which reduces down to 5/2. So that's going to be another answer down here. That would be -12 over 4, which actually comes out as a nice answer. That's -3. So all three of these zeros are rational. We would have been able to test any of those numbers in the synthetic division and found that 0 that way. So we got lucky that the 2 worked right away. This extra one I've put in, so this was not in your review packet originally. I wanted you to see one that only has one rational 0, so that you had to find that one first. That was the only way you were going to be able to break it down. And then the quadratic formula is going to reveal an irrational solution that would not have been in our C over D list. So this is my C's, this is my D's. And again, this one doesn't factor. You could pull out an x squared and you can pull out an 8, but then they don't match. The parentheses don't match. So my C is factors of 8, so that'd be 1, 2, 4, and 8. My D term is 1, so there's going to be just factors of 1. So my C over D list is just all going to be integers. 1 over 2, 1, 2 over 1, 4 over 1, and 8 over 1. So 1, 2, 4, and 8, all plus or minus. I'll start out with 1, because that's where I always start. Pull down the 1, multiply, that's -7. Multiply, that is 9. Multiply, so that's a 1. That's not a remainder of 0. And then try -1. So that's -1, that's -9. Multiply, that's 9. That is 25. Multiply, so we're getting even more farther away from 0. So that's -33. So not working. So I'm probably going to stick with the positives. So I'm going to try 2 next. So that would be 2, and then that's -6, that's -12, that's 4, that is +8. So that comes out to a remainder of 0. I did not plan that. My extra one, I did not plan for it to have the same 0 as the one that was originally in the review, but this one also has a 0 of 2. Okay. The part that's left, remember, would be x squared minus 6x plus 4 equals to 0. We're trying to solve that. So we need, because remember the x minus 2 has kind of been brought out front now, that factor. So we need to solve the quadratic formula for this part. So that'd be x equals -b plus or minus square root b squared minus 4ac all over 2a. So that's 6 plus or minus the square root of 36 minus 16 all over 2. So that is 6 plus or minus the square root of 20 over 2. Square root of 20 has a perfect square that goes into it. That would be 4 times 5, so that's 2 on the square root of 5 over 2. And then this reduces down. This is 3 plus or minus the square root of 5. So my zeros for this one are 1 rational 0 of 2 and then 2 irrational zeros. And again, these two would not have been found using the C over D list. We were only lucky enough to find them because we were able to reduce the degree by 1 when using synthetic division and finding a rational 0. So, you know, sometimes we can solve this all the way down even if it has some nasty answers. That's the beauty of this technique. If you had an x to the 4th as your highest power, we don't usually do that to you on the test because that takes a lot of time to work through 2 rounds of synthetic division to find your zeros. But the thing to note about that is if you did have like an x cubed here when you were still here, you can make a new C over D list, and we highly recommend that using the new C and the new D. Also, never underestimate the multiplicity thing. If a 0 works once, you should always check it again if you're doing a second round. So even though we're not testing you on that, that's good things to know and be aware of. Okay, so that puts us into our last group here of problems. These are from 4.5. Find the vertical, horizontal, and oblique asymptotes, if any, of the rational function. Write none when applicable. So we're looking for, do we have vertical asymptotes, horizontal asymptote, or oblique? Just kind of abbreviate that. So to tell if you have vertical asymptotes, you need to be able to factor the denominator and the numerator. So factor everything. So this factors into x minus 2 and x minus 3 because they have to multiply to +6 but add to -5. So as long as nothing in the bottom cancels out, because if it cancels out it would be a whole, it's a vertical asymptote. So there's 2 vertical asymptotes here. We set them equal to 0 to get the equation. So x equals 2, x equals 3. For horizontal asymptote or oblique, because you can't have both at the same time, it's either one or the other, it's all about whether or not you can do long division. Some people have, there's a shortcut rule about the degree of the top and the degree on the bottom, but essentially it is really just long division. If you say x squared minus 5x plus 6 into 2x squared, I know that's only one term, but x squared does go into 2x squared 2 times. So whatever number or thing you get on top, that's your horizontal or oblique. If it's just a number, no x needed, it's a horizontal asymptote. If it has an x required, it's going to be an oblique. So what that actually boils down to is that if the degree on bottom is smaller than the degree on the top, you're going to be able to get an oblique. If the degree is the same or it's bigger in the bottom, you're going to have a horizontal asymptote. So if you have a horizontal, you're not going to have the oblique. So let's do this next one. So first thing, we're going to factor out anything we can factor. So this is 3x squared, and that would be x minus 2 over, this would be x minus 2, x plus 1. So this cancels right here because that's going to be a whole. Anything that cancels out is a whole. And then this leaves me with 3x squared over x plus 1. So my vertical asymptote is anything left in the bottom after canceling, set it equal to 0, so that would be x equals -1, because remember this guy's going to be a hole in our graph. Horizontal or oblique, that has to do with the long division again. You can use the new reduced function or you can go back to the original. Either way, I usually like to use the reduced version for the long division. And this time we do actually need to ask, x goes into 3x squared. How many times? It'd be 3x. And you need to go the rest of the way to see if there's anything else you need up there. So 3x times that is 3x squared. 3x times 1 would be 3x. And then we change the signs. And then this has to go one more time because we can put x into -3x. That'd be -3, multiply by the front, and then change the signs. Now the remainder that's just a number at the end doesn't matter, but this top part is your y equals mx plus b, because an oblique asymptote is a slanted line for us. We're not doing any quadratic obliques. So that means that this is none. So this is just how you find the oblique. You do the long division. And the reason I knew this was oblique from the beginning is the degree of the bottom was smaller than the degree of the top. So that means I was going to get an x when I did long division. Okay, so then the last two are just graphing completely. So they are longer problems, but we're going to go through it. The things you'll want to know when you're graphing a rational function. You're going to want to know the domain, vertical asymptotes, x-intercepts. We'll walk through each of these steps. Y-intercept. Now all of this is if they exist. We'll want to know if it has a horizontal or if it has an oblique, and if it has a hole. That's the other thing we want to know. Okay, so domain, to find domain and everything else, the first thing we do is we factor everything we can. So this would be x plus 2, x minus 2. Whether or not something cancels on top with something on bottom, your domain is everything in the original denominator. We need to throw those out. So x cannot equal -2 or 2. Those are undefined values. As long as none of those cancel out with anything on top, which they don't since there's no matching binomials, then they're both also vertical asymptotes. X-intercepts are found by setting the top equal to 0 and solving for x. There's no x on the top, so we can't solve for x. So that means there are none for x-intercepts. The y-intercept is found by plugging in 0 for all the x's. So that would be 4 over 0 squared minus 4. So that's going to be 4 over -4 or -1. So 0, -1. Horizontal or oblique, remember that has to do with long division, but x squared cannot divide into 4. So that means it goes 0 times. If it goes just a number without an x, it's a horizontal asymptote, so y equals 0. That means it's none for the obliques. And then since nothing canceled out, no binomials on top and bottom canceled out after factoring, there are no holes. Okay, so that's all the information you have to have up front. Then we want to graph this. Now we'll probably still need to get some extra points to get a good shape of what this is going to look like. But we've got some boundaries in place at least. The good thing about a vertical asymptote is you can never cross the vertical asymptote, so you know that you're kind of stuck right up against those. Horizontal or oblique possibly can be crossed. There's a way to tell that. I'll show you that in just a minute. So I'm going to plot what I know. So 0, -1 is a y-intercept. I have vertical asymptotes at -2 for x, so that's a vertical line at x equals -2. I have one at x equals +2. And then I'm supposed to have a horizontal asymptote at y equals 0. So I'm doing kind of a green line. It's kind of hard to see that. So that's y equals 0. This is x equals -2. And this is x equals +2. Okay, so what you see is that gives me 6 little subregions of this graph. If you look at your green and your blue, I have an above and below on the left side of -2. I have an above and below on the middle between the two blue lines. And I have an above and below on this right side of x equals 2. I typically plug in some x values from each part to see where I'm going to be, either above or below that green line. Now, like I said, sometimes you can cross your horizontal asymptote, so we're going to double check that. So here's how you check if you cross your horizontal or oblique. horizontal, or oblique. You set your original function equal to the value of that asymptote. So 4 over x squared minus 4 equals 0. You cross multiply to solve. That's just going to be 4 equals 0. If you can't solve for x, then it doesn't give you anything. So if you think about that as being over 1, you can cross multiply. There's no x left, so that means no, we don't cross. That's good to know because that means if I find a few points, I know that I'm stuck inside these little boundary lines. So I'm going to do a little table of values and plug in some values on each side of my, this is how I pick. If I have a vertical asymptote or an x-intercept, I make sure I get points on each side of it. We have no x-intercepts, so I'm going to pick points on each side of these blue lines. So I'm going to pick maybe -3, -1, because that's that vertical asymptote. -1 and 1 are both kind of in the middle here, and maybe +3. And we could also do -4 and +4. Then all we do is we plug them into our original function. So we can do most of this one by hand, or just talking through it. The next one we'll probably need the calculator. So -4 squared is 16. -4 is 12. 4 divided by 12 would be 1/3. -3 squared is 9. 9 minus 4 is 5. So this is 4/5. -1 squared is 1. Minus 4 is -3. So that's -4/3. 1 squared is 1. Minus 4 is 3. So that's again -3. Sorry, that's -4/3. 3 squared is 9, minus 4 is 5, so that's going to be 4/5. And I'm guessing this is also going to come out to 1/3, and it does. So there's kind of this symmetry here. So -4 is at 1/3. -3 is at 4/5, so a little bit higher. But because we know we don't cross our horizontal asymptote, and we can never cross vertical asymptotes, we know that this graph, that doesn't really touch that, is kind of hovering into this region above the x-axis. -1 is -4/3. +1 is also -4/3. And we've got this y-intercept. So we know that this graph is kind of stuck in this boundary down below because it can't go back up and cross its horizontal asymptote since we've already proved it doesn't. And then 3 is at 4/5 and 4 is at 1/3. So again, we get this kind of mirror image on this side of what happened on the left. So there's my graph for that function. Okay, let's look at our very last one, so number 21. For the following function, state any vertical, horizontal, or oblique asymptotes, holes, if they exist, and then graph the function. Oops, hang on just a second. Computer's having a little bug. Okay, so then let's factor this one. It looks like this factors onto x minus 5 and x plus 2 on top. Multiplies to -10, adds to -3. The bottom is two perfect squares with a difference, so that'd be x plus 5, x minus 5. So there is a cancellation here. So that's x plus 2 over x plus 5 as the reduced version of this polynomial. Now your domain, though, is what were all the values that were bad from the beginning, and that would be -5 and 5, because they both came from the denominator. The difference here is that there's only one vertical asymptote, because only vertical asymptote is what's left if it doesn't get canceled out. So that would be x equals -5 if we solve that for 0. I'm going to go ahead and write the whole here because it's affected by this. The whole comes from what the part that cancels out. So x equals 5 is a whole because it canceled out. So when we want to know what the whole's ordered pair is, because a whole is not just a whole, it's an ordered pair, we plug that into the remaining function. So 5 plus 2 over 5 plus 5 is 7 over 10. So there's a whole at +5, 7/10. And then the x-intercept, so I'm kind of going a little bit out of order this time, is anything left on top that didn't cancel out. So if we solve that equal to 0, that's -2. So -2, 0. To find my y-intercept, I need to let 0 go in for all the x's. You can either do that in the original function or you can do it in the reduced function if you didn't make any mistakes. If you do it in the original, you get -10 over -25 because everything else becomes a 0, and that reduces down to 2/5. So it is 0 2/5. So that's found by putting in 0 and reducing. So 0 squared minus 25 is -10 over -25, which divide both by 5, and you get 2/5. Okay, so we also need our horizontal versus oblique. Which one do we have? And I think that's it. So we already did the whole. So if we look at horizontal versus oblique, because we can't have both, we try to do long division. So x squared minus 25 into x squared minus 3x minus 10. X squared goes into itself one time with no x's on top. If that happens, you don't need to go any further. It's a horizontal, and it is that value. So y equals 1. So there are none for that. Another way of that is if your power on top and your power on bottom, your leading coefficients powers are the highest degree and they match, the leading coefficients in front of those is the horizontal asymptote. So 1 over 1 is 1. So there's a couple ways you could figure that out without just doing the long division. Okay, so let's graph everything we know so far, and then we will, if we need extra things, we will find extra points. So let me scroll this down just a little bit. So if I take my graph, and let's place horizontal and vertical asymptotes and x and y intercepts wherever we need them. Okay, so the vertical asymptote is at -5. 1, 2, 3. X equals -5. The horizontal asymptote is at +1. The hole, I'm going to go ahead and draw that in. There's a hole at 5 7/10. So 1, 2, 3, 4, 5. Not quite at 1, so that's an open circle there. X-intercepts, -2 is a place we're allowed to cross the x-axis, and 2/5 is a y-intercept. We do need to check to see if this is going to cross its horizontal asymptote, because right now I have tons of points on the side over here across from the -5. It looks like I'm stuck down in this bottom region, but I want to make sure. So you set your original function, which was x squared minus 3x minus 10 over x squared minus 25, or you could use your reduce, but I like to go back to the original because I didn't make any mistakes yet. You set that equal to your horizontal asymptote's value. You cross multiply, and you solve this. So if we try to solve this, we're actually going to get a value here. So this would be -3x. Add that over, that's -15. That's x equals 5. So that's saying we cross at x equals 5, which I have a hole there. So hang on just 1 second. Let me see if I did any arithmetic wrong. I'm sorry, I misspoke. You set the reduced part equal to the horizontal asymptote. So that was x plus 2 over x plus 5 equals 1. If you cross multiply on this, you get x plus 2 equals x plus 5, and that solves to just 2 equals 5, which doesn't have an x value left. So no, we don't cross. Sorry for that. And then we need to look at some extra points. So I need some extra points on the other side of -5. So I'm going to do, let's see, let's do -7, -6. I have a bunch of points, and I also do, so that's my vertical asymptote. If I have an x-intercept, I also pick points on both sides of it. So I'm going to pick -3 because -2 is my x-intercept, and then I already have lots of points on the other side of that. So I know that 0 had a point, and I already know that 5 was a hole. So we have enough information over here on this side, and 0 was 2/5. So we just need some extra points right on this left side of the red line and somewhere in between here to make sure that this is still heading down. So -7, if I plug that into my reduced part, so -7 plus 2 over -7 plus 5, that'd be -5 over -2, or 5/2. If we do -6 plus 2 over -6 plus 5, that is -4 over -1, or just 4. If we do -3 plus 2 over -3 plus 5, that'd be -1 over 2, so that's -1/2. So let's plot what we know. So -7 is at 5/2, that's 2.5. So that would be right here. And then we have -6 is up at +4. So that would be here. So it looks like on the left side of our red vertical asymptote, we're in this upper quadrant part. We're up here in the top boundary of these. And then -3, -1/2 shows me that we are headed down here, and we're headed this direction here. And we don't actually include the hole, so don't draw it in, but you just go kind of on both sides of it. And that's it. So that's the end of the review for this test. Hopefully this is helpful for everybody. I'll be doing one big one when we get to the review for the final, so look for that in the near future.